Sure. All right. Right. Hello, everyone. Welcome to the RSMA webinar series 2023, organized by IEEE Communication Society WTC SIG a special interest group on RSMA. So my name is Won-jae Shin, an associate professor at Korea University, South Korea. So this is our second webinar series this year, and it's our great honor to have Professor Theodoros Tsiftsis from University of Thessaly, Greece. So let me introduce Professor Tsiftsis. So he received bachelor degree in physics from Aristotle University of Thessaloniki, Greek in 1993. Sorry about my poor
No worries.
pronunciation.
I think it's very good.
A master degree in digital system engineering from the Heriot-Watt University, UK in 1995, and another master degree in decision science from the Athens University of Economics and Business, Greek in 2000, and the PhD degree in electrical engineering from the University of Patra, Greek in 2006. So he's a professor of wireless communications in Department of Informatics and Telecommunications at the University of Thessaly, Greek, and honorary professor at Shandong Jiaotong University, Xi'an City, China. So his research interests fall in the broad area of the communication theory and wireless communication with an emphasis on reconfigurable intelligent surface and rate splitting multiple access and optical wireless communications and physical layer security. So Dr. Tsiftsis served on an editorial board on IEEE TCOM and TMC and TVT and IEEE Communication Letter. And he currently serves as an associate editor of the IEEE TWC, and he was appointed as an IEEE Vehicular Technology Society Distinguished Lecturer for the last 2 terms. Let me briefly share our ground rule of our webinar. And so we will have the 15 minutes. So during the talk, you can mute it but you can type your question if you have in the chat box. So after the talk, we will have the 10 minutes Q&A session. So if you have a question, you can unmute it, self-unmute it, and otherwise I can pick 2 to 5 questions from chat box later. Right, I think that's all I have to share. So I hope all of you enjoyed the talk. So yeah, let me stop sharing here. So Professor, you can share your screen if you.
Yeah, Professor Shin, thanks for the introduction. Let me share my presentation. Is it okay? Can you see my presentation?
Yeah, perfect.
Okay, let me just remove the tab for. Okay. Again, thank you for the invitation for this on this RSMA webinar from the IEEE Communication Society, and specific special thanks to Professor Bruno Peltz. Today, good afternoon to all of you, or good evening if you are in Asia. My name is Theodoros Tsiftsis. I'm professor at the University of Thessaly. And today my talk is about cognitive radio-inspired rate splitting multiple access. So this is the structure of my presentation. Actually, I have gathered material from 3 papers published from 2020 until today. So the first one is about rate splitting for uplink NOMA with enhanced fairness and outage performance. We're going to study, I'm going to present you 2 techniques. The one is about the rate splitting with fixed power allocation, and the other one is with cognitive power allocation. The second part is about a new rate splitting strategy for uplink cognitive radio-inspired NOMA system. And the third part of the research results refer to the RSMA-added mobile edge computing with randomly placed cognitive users. In the fourth part of my presentation, I'm going to give you some concluding remarks on CR-inspired RSMA, and finally, some references. Now, the first part is about the rate splitting for uplink norma with enhanced fairness and outdates performance. I would like to emphasize here that this paper is a little bit old, 3 years old, but it's good in order to start studying the uplink non-orthogonal multiple axis. So the in uplink normal systems, signals from multiple users are naturally superimposed at the base station, and we have different path losses in channels, and we use non-orthogonal multiple axis in order to increase the sum rate and achieving user friendliness. On the other hand, rate splitting and its applications for delayed limited transmissions in uplink norma, it's a practical way in order to achieve the capacity region of the multiple axis channels. However, we have here this critical challenge. The challenge in delay limited transmission is that the target rate and transmit power allocation are very important to maintain user fairness and improve outage performance. But we have two problems. The first one is that the current rate splitting schemes, specifically with heuristic or exhaustive setting strategy, they are very computational complex. And the second one is that in the uplink norma, we have the peak to average power ratio and imperfect synchronization issues. So the solution to that will be to implement in the uplink normal system cyclic prefix single current transmissions. So in this first part of my research result, we have a very simple system model that actually involves a base station. Sorry, let me take my laser pointer, that would be easier for you. So we have a base station where the near user U1 communicates directly with the base station. We have a far user U2 that actually also communicates with the base station. And we have the channels H1 and H2, where the channels, we're talking about frequency selective channels. That's why we use the cyclic prefix single carrier transmissions. So the near user U1 and the far user U2 are actually paired and share the same time frequency resource block. I also have here all the parameters like the small scale fading in psi, the number of symbols in its block, and also in order to prevent interblock symbol interference, we have this cyclic prefix part in the symbols we've seen here up in the upper part of the slide. And also, we assume that the far user signals always arrive at the base station after the signal from U1. So there is a kind of time offset M between the two signals. Now, regarding the system model, we can extract by studying the signals in the frequency domain and using frequency domain equalization, we can extract the SINR for the user one, where the signal from the far user is actually treated as a noise, which is in here, the P2H2 squared, and the SNR for the signal of the second user, gamma 2. And at the bottom of the slide, you have the equivalent SNR is the parameter rho. The epsilon parameter is the constant reflecting the large scale fading disparity between two users. And this calligraphic L is actually the path loss, which is associated with the frequency selective fading channel. I would like also to, I would like to say here that when the signal actually is received at the base station, frequency domain equalization is actually applied for detecting first the near user signal, and then the reconstructed signal is subtracted and with the compensation of FDE, we estimate X2. So here we're going to implement two new schemes of rate splitting. The first one is about, we assume fixed rate splitting for the near user, the FRSN, and the fixed rate splitting for the far user. So it is also known that for the multiple access channels with two users, only one single user signal needs to be split to achieve the capacity region. And this is actually it's a result that has been taken from this paper at the bottom of the slide. And it's well known on the research community who works on rate splitting multiple access. So in the fixed rate splitting at the near user, we have the received frequency domain signal at the base station. Alpha is the power allocation factor. And here we have the targeted data rates, R11 hat, which is B times the R1 hat, and R12 hat, where B is the targeted data rate factor. Let me remind you regarding the achievable rate region. So I have a graph here where we've seen the achievable rate region for orthogonal multiple access, OMA, NOMA, and NOMA with rate splitting. As we've seen here, in order to determine a suitable decoding order for the FRSN scheme, we have the achievable rate region here, and it is compared with OMA and NOMA. As you see that the NOMA, the current points alpha and beta are achieved. Here's the beta achieved by the conventional NOMA with SIG, while any rare pairs on the line segment can be actually attained with the rate splitting multiple access. Also in this graph, we have the two cases. I mean, the first one is for asymmetric channels, and the other one, the other region is for symmetric channels. So the point A, B, and C in these graphs is actually the decoding order. So the point alpha, the point A is actually X11, X12, X2. So the X1 signal is split into subsignals. A point B started from X2 and the point C from X11. So here I have the decoding order for FRSN, which is quite simple. I mean, X1 is split in X11 and X12. Then you've seen here that when the signal is received, the Y signal received, then we have the detection and the modulation of X11, and then we estimate the SINR for gamma 11 for the near user. And then this signal is actually subtracted from the overall signal. Then we get the detection and the modulation of X2. We get the SNR of X2 of the user 2 here. And then this is also subtracted from the received signal. And then we get the second part of the signal X1, I mean X12, and we get the SNR for gamma 12. This is for the near user. And this is also for the far user. I mean, it obviously, we use now the rate splitting for the second user. So we have this kind of decoding order. And again, we have the detection and modulation stages, the 3 stages, and we get the SINR and SNR for gamma 21, gamma 1, and gamma 22 for the far user. That's why I have this parameter F, where you've seen in order to differentiate from the near user, we've seen in the previous slide. However, in order to have this kind of fairness between users, then we use a very well-known fairness index, which is called James Fairness Index. However, in the sense of James Index for measuring the user fairness, it actually has been shown that the corner points achieved by NOMA with SIG is fairer than NOMA. okay, this is something well true. But unfortunately, the commonly adopted, this one is the commonly adopted James index, is defined in terms of achievable rate per channel use, while each user in the delay limited transmission mode actually transmits a fixed transmit rate corresponding to each quality of service requirement. Considering that the fairness in delayed limited transmissions is actually affected by not only the quality of service requirements, or the quality of service of the user's requirements, but also the average throughput. That's why here we have proposed, we proposed a modified fairness index. And by having the SINR and SNRs for the near user and far user, then we are ready to extract the outage probability for the user 1 and user 2, both for the near user and the far user. Actually, here in this slide, I just give you only the outage probability in terms of probabilities. However, we have some theorems in this paper where the above outage probabilities are evaluated in closed form expression, but I'm not giving here because I have to spend 2 or 3 slides to show the final expressions. So what happened to the fixed rate splitting is something that actually, I mean, it's more or less is known. So we go to the cognitive rate splitting. So we assume that the users U1 and U2 are actually treated as the primary and secondary users in the sense of the underlay cognitive radio. So we have now the 2 schemes, the cognitive radio splitting CRS for the near user, which is actually the primary user, and the CRSF for the far user. However, there's a big difference with the FRS schemes that the power allocation factors of CRS schemes are actually dynamically determined based on the standard challenge gains. Because we have, I mean, this is something that can be easily understand because we have the interference temperature with this kind of limit in the primary user. So in that case, the targeted data rates for the split data stream need to be predefined because we consider delay limited transmission. So for the now in this slide, I just show you the decoding order and the power allocation factor we have for the cognitive radio splitting for the near user. So the decoding order is still, again, we split the primary users signal. So we have X11 to X2 to X12. We have evaluated the cognitive power allocation factor, where the cognitive power allocation factor is actually dependent on the threshold and the free temperature of the primary user. So this is so the power allocation factor is actually the maximum of these 2 alpha hat and alpha tilde power allocation factor regarding some specific constraints on the targeted SNR. So we have we set a theorem here about to evaluate the outage probability for the CRSN for the user 1 and the user 2. I mean, the primary user and the secondary user. So we have closed form expressions for both outage probabilities. So it's something that we can easily calculate it. The second scheme, I mean, the CRSF, now the split is actually goes to the secondary user. So it's X21, X1, X22. So we apply this kind of decoding order. And we have some new cognitive power allocation factors that's given in the middle of this slide. So again, we follow the same mathematical analysis, and by defining a new theorem, we actually calculate the outage probabilities for the user 1 and user 2. Again, both expressions are given in closed form. Let's go to the some simulation numerical results. This is the first slide where we have the outage probability versus the signal to noise ratio, the transmit signal to noise ratio of the user 1 and user 2. So we've seen actually what we get from this from both figures is that the FRS and schemes and the CR and the CRS, the cognitive radio CRS schemes are always provide better outage probability compared to the NOMA scheme, which is NOMA is given in here with the orange color, and FRS and CRS schemes decrease the outage probability, specifically in the middle and in the high SNR region. For example, we see in the U1, the NOMA is better in the low SNR region. Here's a graph about the fairness index against versus SNR. So we've seen here that in the middle and the high SNR regions, all the FRS outperform NOMA scheme. And also we've seen here the lowest SNR case that the CRS schemes provide less performance compared to the fixed rate splitting. And the third, we have another set of graphs here, which is about the outage probability against the rate splitting factor and power allocation factor. So we have the power allocation factor, which beta is the first one here, and alpha is the power allocation factor. So the FRS and CRSN for the near user achieve the smaller outage probabilities than those when the FRS and CRS are evaluated for the far user. And this is due to the strong channel gain associated with the user 1. All the schemes cannot correctly detect the desired signals in the high beta region, the high RS factor, where the corresponding target rates gamma 1, gamma 2, are too high to be satisfying. This is, this is because increasing beta can be regarded as increasing the error propagation in SIG processing, okay, in successive interference cancellation. It's something equivalent. And also where the FRSF and FRSN schemes are applied, alpha should be chosen to guarantee a desirable outage performance for both users. We've seen here that in this graph that the CRSN and schemes achieve the smallest outage probability compared for both users U1 and U2. This is the second part of my presentation, and it's about the, in 2020, last year, we just published a paper with my co-authors in the I2D TBT, which is about the new rate splitting strategy for uplink CR NOMA. So we know that the problem exists in the successive interference cancellation and power control schemes that cannot fully achieve the capacity region of the uplink multiple access channels. And this is because the decoding performance of NOMA receivers strongly depends on how the SIG decoding order has been set and the associated or optimized, and how also the associated power control has been optimized. So according to the power domain NOMA, we get some suboptimal outage performance. So the solution is to, we propose a new rate splitting strategy by employing an uplink CR-inspired non-orthogonal multiple access. And at the same time, we don't deteriorate the outage performance of the primary user compared to the orthogonal multiple access. So the SU splits its signals into streams and allocate its power efficiently in order to maximize the achievable rate. So the system model, again, is very simple. It's a two-user model. We have the primary user U sub-0, and the U1 is the secondary user that actually transmits directly to the base station. And we have the H0 and H1 is the fading channels. I have here all the parameters. I mean, the PI is the transmitter power, the channel gain, the target rate, which is that I had, the interference threshold, the power allocation factor. And also at the bottom of the slide, I have two papers where it will be used as benchmark results compared to the results we published in this paper. And the one is a paper from Zewedin regarding quality of SIG, quality of service, success with interference cancellation. The other one is about the new harvesting SIG method. Sorry, a new hybrid SIG method. Now, according to the system model, the user one splits its signal into X11 and X12. And the secondary user transmits its signal X0. So what is received at the base station? It's very simple. It's this expression here, the expression, the Y signal. And we use the very well-known SIG decoding order, X11 to X0 to X12. And I just give you here the SINR and SNR and achievable rates we get from these actually transmissions. So the new RS strategy concept is designed in order to maximize the achievable rate of the secondary user, where the secondary user is R1, it means R11 plus R12. But at the same time, to keep the primary user, to keep its performance with the same outage performance as in the OMA scenario. So to maximize the achievable rate R1, the strategy is to maximize the R12, considering that the detection of X12 signal is interference-free in the successful interference cancellation signal processing method. So the concept, our concept of the rates of this rate splitting strategy is actually involves three different cases. The first case is the interference threshold is greater than 0, and the transmission from the secondary is less than this threshold tau. The third, let's go. I'm going to the third one because what we propose as new is the second one. The third case is when the threshold is 0, and when the threshold is greater than 0 and the transmission from the secondary unit is greater than tau, then the achievable rate for this case is this one here. But in that case, we have to ensure that the primary user achieves the same outage probability as OMA. But in order this to be happen, then the successful detection of X11 before detecting the X0 is absolutely necessary. However, I say here that X11 cannot be detected correctly if the second case rate is less than the rate is needed in order to have a successfully decoding. Therefore, in this strategy, U1 is allowed to transmit only if the the rate of the second user is always greater than the targeted rate of R1. Otherwise, the primary user, otherwise the secondary user keeps silent. Now, let's go to the mathematics now. As I said before, we study here also the outage analysis. And we have to keep that the primary user experiences the same outage probability as in the orthogonal case. And the outage probability that is experienced by the secondary user is given by this expression here, which is actually the sum of the two outage probabilities, where the outage probabilities are analyzed at the bottom of this slide. So in two theorems, theorem 1, we evaluated the outage probability for the second case, which is new. And in theorem 2, we just evaluated for the case 1 and case for the scenario 1 and the scenario and the third scenario. However, as I said before, we need to compare what we propose with some previous published results. And the one is with the one published by the paper from the ZWD, which is about the quality of service success with the first cancellation, and another one which is a new hybrid SIG method. So, however, QoS SIG and NHS SIG in case 1 and case 3, they derive exactly the same results as in our strategy. But for the case 2, these methods, we get the rate and the outage probability for the secondary user in expressions given in this slide. So there's a difference, for example, between the NHS SIG method and the method we actually proposed. And our proposed method actually provides less outage probability compared to the NHS SIG. So it's actually improves the outage probability of the system. And here we have evaluated with a simple subtraction the difference between the two outage probability only for the NHS SIG. Now, results regarding the outage probability. So now we actually compare what we proposed with the previous two QoS SIG and NHS SIG, and also in order to enhance, in order to emphasize more that the validity of our RS strategy, we involve also another method, which is an old paper published back in 2013. It's the CSI. We just noted that as CSI SIG. So we've seen that in contrast to CSI SIG and quality of service SIG that cause error floors, they're up there, our strategy achieves the lowest outage probability, which is actually the proposed scheme is the purple curve. Okay. However, after the from middle to highest in our region, then the NHS SIG scheme and our proposed strategy actually provide the same outage performance. In the highest in our region, the proposed scheme and the NHS SIG scheme, as you see here in these two curves, achieve the same outage probability because the difference actually tends to 0. And here we have two graphs for the outage performance of U1 and the second case. One is about with the transmitted SNR, and the other one is with the targeted rate. So the the results in, it's in figure, the first figure on your left side of this slide is, I think it's similar to the previous one. It's quite easy. I mean, our strategy is much better than the NHS SIG or the CSI SIG, which actually they provide a kind of error for here. And what is it's important here is the results in the second figure, where we see also that the conditional outage probability achieved by all procedure schemes monotonically increases with increasing target rate. So among the four schemes, the proposed one achieves the lowest conditional outage probability, as we see in both figures. And the last figure for the second part, which is about the average throughput given in bits per channel views against the transmitted SNR. Again, we noticed that compared to the CSI SIG, QoS SIG, and NHS SIG, which are used as benchmark solutions, the performance of the secondary user achieved by our proposed RS scheme is much greater in the middle and the highest SNR region, as we see in this graph. And this happened because the proposed RS scheme exploits the transmit power much more efficiently compared to the previous to all benchmark schemes. And let's go to the third part of our work, which is the core part of the presentation. It's about an almost new work that's published in last May 2023. It's about RSMA aided mobile edge computing with randomly placed cognitive user. It's a paper that's been published in IEEE Journal of Selected Areas in Communications. For the history, we know that the goal for the uplink rate split multiple access for more than 2 users, the goal is to maximize the sum rate of all users with proportional rate constraints. And RSMA, as we've seen here from the capacity regions, we've seen that when we have a non-orthogonal multiple access, we have an outage zone where this is actually we alleviate this problem by using the RSMA. So the goal with uplink RSMA is to enhance the outage performance at the fairness between users. Here we started a kind of different problem where it's about the RSMA assisted mobile edge computing. So we have the MEC server, which is actually the base station, and partially the tasks from users are offloaded to the MEC server, and the remaining parts of the tasks are executed locally to the user. So, so what we did here actually is that we combine the benefits from the mobile edge computing and the cognitive radio in order to enhance the performance of RSMA. So the motivation is similar to what we just discussed in the previous slide, that the adopted NOMA, we say we cannot achieve the full capacity region in the uplink multiple access channels. We should use the exhaustive search in order to find which is the optimal decoding order. This is something very complex. And also, to apply RSMA for uplink multiple access channels is something very beneficial, because we have this kind of effective of interference management. So the solution to, according to the motivation, the problems we study, we propose an uplink CR-inspired RSMA-aided mobile edge computing scheme, RSMA MEC scheme, to increase the computational probability we'll discuss later on what is the successful computation probability, and reduce the offloading latency to the MEC system. Also, in our study, we get also the user location. So the user location, where the user actually is located, is very important and is paramount because it has an impact on the channel's conditions. And we actually model the user location. We more involve by using the heterogeneous Poisson process stochastic geometry to the RSMA MEC scheme, and thus we studied the problem from all sides. So here is the RSMA system model that has been proposed. You've seen here the MEC server. You've seen in radius RC, you've seen all the center users, which is we use as a triangle for the symbol. And the edge user is actually located to a disk which has radius of RE. And U alpha is the primary user, and UB actually is the secondary user. The secondary user is actually located in on the edge, and in the center we have the primary users. And you've seen here that all the process is actually should be finalized in a budget period of capital T, and the capital T should be less or equal to the channel coherence time. So in this actually budget, we have the time, the T1 time for the parameters determination, power allocation factor, rate splitting factor, offloading factors, etc. We have the second part, which is the task offloading by U alpha and UB to the MEC server. We have the third part of the time, which is the task where the necessary computation task needs to be executed at the MEC server and also locally to the users U alpha and UB. And finally, in the last part, T4, we have where the results are downloaded from the MEC servers to the users. Now, the first phase, which is, we're not going to discuss the T1, which is the preliminary determination of the factors of the power allocation factor, rate splitting factor, or the T4, and because these two period of times are much less than the T2 and T3, which are the offloaded time and the computational task time. So the received signal at the MEC server from any pair of primary and secondary users given by this expression. Alpha is the power allocation factor. We use this kind of SIG decoding order. It means that we split the secondary users methods XB1 to X alpha to XB2. And we have here also the received SINR or SNR for all the detected symbols at the base station / edge server. And also the parameters rho alpha and rho B, which denote the equivalent transmit signal to noise ratio. So the offloaded task bits from the user alpha or user B is given from these expressions here. We have also with RA hat and RB hat, we denoted the target rates, where beta is the rate splitting factor, and eta k is the task offloading factor per user. And the total number of task bits actually offloaded to the MEC server is given by expression at the bottom of this slide. Now let's go to the next phase, which is the task execution phase, the third phase, where we consider a hybrid offloading scenario that includes partial offloading, fully local computation, eta kappa is 0, or complete offloading where the eta kappa is equals to 1. And we have also the remaining parts of that should be computed locally at the user's U alpha and UB. So the execution time, T3, is actually the maximum of the execution time needed per user, U alpha or UB, and also the execution time per MEC server. And here also we use in this expression the CPU frequency of the MEC server, which is much greater than the CPU frequency of per user. So the CR-inspired rate splitting procedure is quite easy. Again, because we have a cognitive radio inspired RS system, we assume that we have interference threshold to the primary user, and we, as I said before, we use this kind of cognitive order. I would like to make a remark here that the primary user feeds back its CSI and its parameter of the transmission power to the MEC server after estimating the CSI. So the CSI is fully aware of the CSI in P alpha. And the MEC server calculates the interference threshold and then broadcasts this interference threshold to the secondary user at T1. So the secondary users compare the interference threshold to its current CSI, and according to this comparison, determines what is the optimal rate splitting factors in order to start to split its signal and start the transmission. As we did in the second part of the paper, also in this CR-inspired RSM design, we have three cases. The first case is when the secondary user transmits with it's less than the threshold, the interference temperature threshold. So these are the bits are actually offloaded to the MEC server. And the optimal power allocation, the rate splitting factor in this case, both are 0. And we have also calculated what are the maximum task bits that offloaded to the MEC server, both from primary user and secondary user. We did the same for the second case when the parameter tau is less than the transmitted SNR, and again we have evaluated the offloaded task bits which are given from these expressions here. In that case, the optimal power allocation and rate splitting factor is different and not 0. They have some another value that it can be evaluated according to the CSI. And the maximum task bits for the case 2 are given by the expression at the bottom of this side, and referred the R alpha bar is for the task bits offloaded from the user alpha or primary user, and RB bar is for the secondary user. And the third scenario, when the tau is actually equals to 0, in that case, the primary user cannot successfully offload its task bits to the MEC server because the channel conditions between the primary user and the MEC server are really weak. And in that case, the secondary user allocate all of its transmission power in order to transmit the overall power. In that case, we have the optimal power allocations and the rate splitting factors equals to 1. And again, we have evaluated the maximum task bits that can be offloaded to the MEC server. So in case 1 and case 2 are actually binary, are 0 or 1. The only difference is in the case 2, in the second case. So what insights we get from these scenarios is that the case 1 and case 3, the performance of the primary user and secondary user are actually similar to the two-user NOMA-MEC system. Or, as I said, the optimal rate splitting parameters are binary. However, in case 2, the secondary user adjusts the rate splitting parameters to maximize the offloaded task bits, and this happens according to the CSI per channel. Also, in the second case, the time phase T1, which is the where we actually the MEC server gets the information from the primary user and then forward this information to the secondary user. It's the time phase T1 is actually it's ignored because it's much smaller than the second time period or the third time period. Here we're going to study a metric which is called successful computational probability. And successful computational probability defines the probability of the event that all offloaded tasks are successfully computed at the MEC server, and all the remaining tasks are actually successfully and locally computed by the paired users. So we have the expression here for the SCP under this condition that the third period of time for all the users on MEC server is less than a specific time period, and we evaluate, we get a closed form expression for the successful computational probability, which is given in closed form, okay, in this expression here. And we also maximize, we set a maximization problem in order to maximize, find the optimal SCP according to second time period, third time period, and the offloaded factors at alpha and theta b. However, this problem is non-convex, and that's why we, by using a new proposition, a new corollary, we extract the optimal at alpha and theta b factors, and also the time period 2 and the time period 3. The second part of remarks is that the offloading parameters depend from many things, from computational capabilities of the nodes, the task bits, the latency budget, etc. But it's irrespective of the paired user location. So the results from the maximization problems can be applicable to the RSMA MEC system, containing also the randomly deployed users, no matter what are the locations. So so if we have evaluated the optimal offloading parameters theta alpha and theta b, then the MEC server has stronger computational capability and vice versa. So in order to reduce the latency budget and also to maximize the SCP, we have to evaluate the periods T2 and T3, which is the offloading period and the computation period effectively. Here is the optimal solution of the SCP maximization problem, where you see that the SCP expression involves the CSI statistics and offloading parameters. Now, as I said before, we're going to use the stochastic geometry and the location of the users in order to see what happens when we get pairs from edge of the center and interchangeably if it is primary user or secondary user. For example, if we randomly select from the center and the edge, it's called RCRE. If we randomly select the primary user from edge, it's RERC. So the first two symbols denote if it's far or near, and the second letter of the second letter is if it's from the center or the edge. But the first two refers to the primary user, and the second two symbols refers to the secondary user. So the NE, NC, it means that the nearest user is located in the edge group, and it's actually the primary user, and the nearest and the secondary user is the nearest in the center group. Okay, this is how we use this kind of acronyms in order to understand that we get a specific pair of users, but located either in the edge, either at the center. So we evaluate the primary, when the primary user belongs to the center group, by using the Chebyshev-Gaussian quadrature approximation, the successful computation probability, or from the edge group. So we get, again, closed form expression, but this approximative closed form expressions. And now we have the graphs of the SCP performance versus the computation task bits MB. So it's true here that when the SCP is actually improved when the computational task bits increase, and the RSMA MEC always outperforms the norma MEC scheme, where the norma MEC scheme is given here in the orange curve. For the complete offloading, here is the dashed line is the complete offloading. For the complete offloading, the SCP performance obtained by RSMA MEC scheme is also better than the norma MEC scheme. It's because that the RSMA MEC scheme always takes full advantage, in that case, of the primary user's threshold, tau, in order to obtain a higher achievable rate at the secondary user. Here is the SCP performance and latest against the CPU frequency of the user. So as the F user increases, the latency T budget decreases, and because the T3 is decreased. And however, in that case, the SCP actually keeps constant because the time period T2 and the rate splitting factors eta alpha, eta b remain. Sorry, the offloading parameters eta alpha and eta b remain constant. Here it's about the SCP performance achieved by using pairing schemes, where we illustrate graphs with the transmit power of the user alpha. So in that case, it's always absolutely clear that the proposed scheme performs better, much better than the normal schemes in most of the scenarios, except here, for example, when in all scenarios, except some cases, sorry, here is a successful outage probability, and where the normal scheme is much better for the randomly selected user pair. Only in that case, the normal schemes outperforms for the successful computation probability, while in other cases, the proposed schemes are much, much better. And the last graph, which is about the SCP performance against the ratio of the radius, RE over RC. So on the left-hand side, the RE is kept constant, whereas on the right-hand side, the RC is actually stay constant. So in both cases, one of the radius actually is changing. We noticed that the both RC and RE severely affect the successful computational probability. I mean, it's clearly shown from this graph that when we're changing when the RC is changing or the RE is changing, I mean, we have big changes in the successful computational probability, both on the next server and the locally at the users. Now, I got in the slide some concluding remarks gathered from the three parts, from the three papers that we published. So the first conclusion is that the rate splitting, it's true that improves the user fairness and outage performance for the uplink NOMA scenarios. The cognitive radio splitting for the near user, for the two-user scenario scheme, achieves the best outage performance, specifically for the middle and the high scenarios. The RS scheme can enhance the outage of the secondary user in the uplink CR-NOMA, and at the same time does not deteriorate the outage of the primary user. And the last two is about the RSMA MEC, where the RSMA MEC achieves the maximization of the secondary user's achievable rate, and at the same time, the primary user has the same performance as in the orthogonal multiple axis. And the RSMA MEC scheme achieves higher performance in most of the cases from the NOMA MEC scenario. And of course, it's fully dependent on the locations of the users. Some future research direction is that to extend the proposed CR-inspired RSMA to multiple secondary and primary user scenario, and study the problem over generalized fading channels and sampling conditions. Another problem that it's really difficult is to in order to have simultaneous uplink transmissions and at the same time interference management. And the last one is to extend further the RSMA MEC scenario we study and the latest and reliability constraints, and especially with under the URLC framework as defined in the 5G. Here are the references about my papers. I think that we surpassed the time for 10 minutes. Sorry about that. Thank you for your attendance. Questions?
Yeah, thank you for a very inspiring talk. So we have some questions from in a chat box. So let me read the question from the Aydin, who is also the co-organizer of this RSMA webinar series. The first question from him is, can we say that array splitting is changing the decision on whether the computation offloading is performed or not when compared to NOMA or OMA? I think it's
yeah, I mean, the rate splitting compared to the classical uplink NOMA, it seems to have more benefits. So we actually take into account the CSI conditions, and not only that, but for the cognitive inspired scenario, attains. I mean, it's very beneficial to the rate of the secondary user, but at the same time, would like to keep the performance of the primary user similar to orthogonal multiple axis case. What is very important and analytical, because a little bit difficult, is to include in our scenarios where it's a user actually based. Okay, so we evaluated the probability density functions according to the location per user, but the scenario is only for a pair of users and not a group of users. That would be more and more difficult. So in that scenario, it seems that the rate splitting, it's much, much better. It performs in terms not only of the outage probability, but also for the successful computation probability to the MEC server, and also to the case where it's computed locally. RSMA provides the performance in terms of a physical layer point of view, and also the computational probability. That's why I think that RSMA seems to be a better scenario compared to the normal. I also would like to add something else here, that what is very, very difficult is to find the optimal decoding structure. Okay, the decoding order is something that we have to evaluate it from the beginning. So here in our scenario, we always use it from the secondary user. Okay, but when we started the problem involving the location, then the cognitive user, the secondary user, or the primary user can be near to the edge server or at the edge of the MEC server. So the scenarios all the time are changed. So we have all these kind of parameters. We have evaluated the offloading parameters, so we're able to benefit the system a lot. So that's my answer. I don't know if
yeah, thank you.
Thank you, Professor Aydin. Yeah.
And also he has another question. So
okay,
regarding the plot on the SCP on the slide, so given that NOMA is special case of RSMA, why is NOMA perform better in those plots for some power?
You mean about the successful computational probability, you mean?
Yeah, I think so, yeah.
Yeah, for the successful computation probability, but this is only for the case when the user's randomly selected. Okay, when randomly selected, it seems that it's better. But when we have the RSMA and we use specific pairs, near the edge, the primary user, near the edge, the cognitive user. In that cases, all the other pairing schemes outperform the NOMA MEC. Okay. I'm talking about the successful computational probability.
Yeah.
Okay.
Okay. So the beyond, not if this is not a randomly selected pairing, then RSMA would be
the SCP is much better. It's also shown in these graphs here where we got the successful computational probability and we change the area that is covered by the center group or the edge group. Okay.
Yeah, I think that your answer would be clear for everyone. So, and also, I think there are some attendee who is not very familiar with Omnic RSMA, because many people are also looking at Downic RSMA, and also they are not familiar with Omnic. So, Qiang Yu Feng ask you that it seems that decoding order plays a very important role in Omnic.
Yeah, that's true. Yes, that's true.
However, it's usually
in general, yeah, because I understand what he's actually would like to ask is that the Downlink case is always much better. Okay. And the uplink scenario, analytical also, mathematically, the problems are more difficult and more severe. So that's why most of the people, they work on the download scenarios and not on the uplink scenarios. Okay.
Maybe I have a one very quick question. So, you introduced three reasons your work, and it seems that you're assume that two user pair for the omnic scenario. Can we extend it to the multiple user scenario, and then how we can split the message in that cases?
Yeah, because I have think a little bit. I mean, I haven't solved the problem. I have to admit that because it's mathematical. It's very difficult. The scenario could be, as I said here to my future research direction, is to have multiple secondary and primary users. Then the scenario could be to study the uplink by setting some groups of users, and inside this group to have some other subgroups. However, I think that mathematically is very difficult. We haven't tried yet. I mean, we haven't solved this problem. I don't have something else to show you. If I had, for sure I would. But I think that considering, I mean, this problem for sure is something which is very timely, because we're going from 5G to 5G enhanced and 6G scenarios where we have billions of users and terminals and servers that connected to the network. So in that case, I think that this kind of RSMA uplink scenarios would be very, very challenging. I don't have any, I mean, I don't have an answer, Professor Sim, for that. I haven't thought about it. In order to be honest, I thought about it, but I don't know how I can solve it, okay? If I knew I have published the paper, okay.
Right, thank you. Yeah, I think also the Lena also have a question who is also called this webinar series. So I have one general question. Could you also provide some general insight on a potential benefit of using omnic RSMA for edge AI?
For using, sorry?
For the AI computing, or edge computing, or
yeah, I mean, what actually I forgot to, but I did that on purpose in my future research direction, is to add something about AI, deep learning, machine learning scenario that will be, of course, be very, very useful for, especially for the computation part, for the computational part. Regarding the CSI estimation, regarding the challenge, the physical layer concept, I guess that AI, I mean, deep learning and machine learning scenarios, I mean, machine learning, they don't have much practical interest. It's only for academic papers. I mean, we have very good classical signal processing algorithms in order to estimate the CSI. Of course, we can use the AI part for the computational tasks in order to speed up the computational execution, both at the MEC server and the locally computed tasks of the user. Yeah, this can be a scenario. And it would be a nice extension for the paper, probably. Yeah, at that period, we didn't also, as you know, there are some constraints on publishing papers, so we cannot add all the material in one paper. Yeah, but I just repeat again that it would be good also it would be only beneficial for the computational part, for this, for the rest of the signal processing and estimation of the channels, etc. I think it's quite, AI is quite complicated, and it's very time consuming.
All right, I think that's all our questions from the audience. So thank you for your very nice talk.
Thank you very much. Thank you very much.
Thank you. And also the Q&A session too. Yeah.
It was my pleasure to be here today.
Thank you, Professor.
Thank you.
Yeah, I also would like to tell the audience that the next talk is on the 31st of October, 2023 by Professor Zhao Yang, and he will be discussing the interplay of RSMA and semantic communications. So please join us on the 31st of October.
Anup, thank you very much
Thank you.
for the invitation. Yeah.
Yeah, this was very enlightening. Thank you.
Thank you.
Thank
Have a
you.
good afternoon, evening, or night if you're in Asia. Okay, goodbye. Thank you.
Bye-bye.
Thank you.
Thank
Bye.
you.
See you, everybody.